Hello everyone, can you hear me? Hello, am I audible to all of you? Can anyone please reply whether I am audible or not? Hello, anyone? Hello, hello everyone. A very good evening to all of you. I once again welcome all of you to the interaction session on experimental physics, which is being taught this semester by NPTEL. Myself, Vivekananda Nayak. I am a PhD research scholar at Department of Energy Science and Engineering, IIT Delhi. So let's start with today's session. In last session, we had discussed about different types of oscillations and different experiments related to the oscillations like simple pendulum, compound pendulum, coupled pendulum, like this. So now today in this interaction session, we will be discussing about these three experiments. The first one is the experimental demonstration of standing waves in a string. So we will first discuss about what is called as wave, then the how to measure the frequency or wavelength of the standing wave, like all these things, and from that we can determine the linear mass density of the string. That is, linear mass density means mass per unit length. If L is the length of the string and M is the mass of the string, then mu is the mass per unit length of the M is the mass per mu is the mass per unit length. And then the second experiment is linear expansion of metal. And then the next experiment is determination of coefficient of thermal conductivity of a bad conductor. So first we will discuss about experimental demonstration on the standing waves on a string that has been shown and how to determine the linear mass density of the string. Now, before discussing about the measurement of all these quantities, now first we should know what is wave. So a wave is a disturbance in a medium that carries energy without a net movement of particle. So wave is a disturbance that carries energy without a net movement of particle. It may take form of elastic deformation, a variation of pressure, electric or magnetic intensity, electric potential, or temperature. So basically wave means variation or change in some or periodic change in some quantity which results in the propagation of wave. So basically, if you see, there are two types of waves. Mainly the waves has been classified into two types. The first one is the transverse wave. And what is transverse wave? A transverse wave are those waves in which the medium moves at right angles to the direction of wave. Now, I told you that wave is basically the variation of some quantity. For example, if you take the example of a water wave. Now, also in case of transverse wave, the example of transverse wave is water wave. Now, if you take the example of water wave, here the variable quantity is the height of the water. So now, if this is the plane surface and you disturb the surface by throwing a stone, then there will be a propagation of wave. The water wave will be like this. So this means if this is the h is equal to 0, then here there is some value and here there is some value. So the height of the water above the base height or undisturbed, when the system is undisturbed, is varying. So this variation of height of the water is called as water wave. Similarly, in case of light waves, what we have? We have the variation in electric and magnetic field intensity. So the transverse waves are these waves in which the medium moves at right angles to the direction of the wave. Now, as you can see here, if you take the example here, the wave is propagating along this direction. But if you see the change in height or the particle, suppose there is one particle here, then it is displacing to here. because the height is h here. So the particle is getting displaced by a height of h. So the displacement is along, suppose if this is x axis and this is y axis. So now you can clearly see the wave is propagating along x direction, but the displacement of the particle is along y direction. So for these kind of waves in which the wave propagates at an angle which is right angle to the direction of the actual movement of the particle that constitute the wave. Now this is the example of, now here you can see this is an example of any type of wave. Now if you see there are different parameters of wave. One is called as wavelength, then another is frequency which is called as nu, then another is nu bar which is divided by, which is the reciprocal of wavelength, that is called as wave number, and this is then there is velocity of the wave. So we will be discussing about all these quantities after some time. Now two or three most important quantities of a wave are, one is amplitude. Now for example, for this wave the amplitude is h here. Here the amplitude is 0 and here the amplitude is maximum. So now these give rise to another quantity which is called as wavelength. Now wavelength is defined as the distance between two consecutive maxima, two consecutive minima. So here if you can see here the height is h here. Similarly here the height is minus h here. So now here this is the maxima point and this is the minima point. So wavelength is basically the distance between the two consecutive maxima or minima, or the distance between two maxima, two minima. So here one maxima is here, then the next maxima is here. So the distance between these 2 points is wavelength lambda. Similarly, when talking about minima, there is one minima here and another minima is here. So here this distance is also called as wavelength. Similarly, since the wave is propagating, it has some velocity. So corresponding to that velocity, we can also calculate the frequency of the wave. Now, frequency is velocity by wavelength. So the relation between the physical quantities of a wave is frequency is equal to velocity by wavelength. Now, talking about longitudinal waves, a longitudinal wave has the movement of the particle in the medium in same dimension as the direction of movement of the wave. Now, if you take example of a sound wave, now how sound wave propagate? The sound wave propagate in, like suppose this is the sound wave is propagating along this direction, then we know the sound wave propagates as a result of compression and air fraction of the particles in that medium. So the particle also move in that direction. The particle expand and particle contract, like this they move. So the movement of particle is also along the same direction. This is x direction. So the direction of the movement, the direction of the movement of the wave is equal to that of the direction of movement of the particle which constitute the wave. So this is called as longitudinal wave. So transverse means the we can simply remember that in transverse wave, the particle which constitute the wave vibrate transversely. However, in longitudinal wave, the particle constituting the wave vibrates along the direction of the propagation of wave. Now, if you see for transverse wave, we have a crest and we have a trough. So the high point of a transverse wave is crest. Now this point is called as crest and this point is called as trough. So the distance between two consecutive crests or the distance between two consecutive troughs are called as wavelength. Similarly, talking about longitudinal wave, they pass through the system by means of rarefaction and compression. So these are the two parameters which are involved in case of longitudinal wave. Now we all know that light, which is an electromagnetic wave, is also transverse in nature. So if you see, we know electromagnetic means it has electric field and it has magnetic field. So the name is electromagnetic field. So as you can see, the wave is propagating along this direction. That is, if you compare, suppose this is x, this is y, and this is z. So if the wave is propagating along x direction, the electric field is varying along y direction and the magnetic field is varying along z direction. So if the wave, suppose this is the wave which is given by This is called as wave vector. So wave vector is basically, now we know lambda. Lambda is the distance between two minima to maxima. Similarly, if you talk about wave vector, then it will be 2 pi by lambda. So 2 pi by lambda will be k. Now this is called as wavelength. So this is called as wavelength, and this k is called as wave vector. Similarly, 2 pi by nu is, sorry, 2 pi by t. 2 pi by t is omega. This is time, and this is angular frequency. So if you see, the k vector is along x direction. That is, the movement of wave is along x direction. So the wave is moving along x direction, and the electric field varies along y direction, and magnetic field varies along z direction. So here, the electromagnetic wave is an example of a transverse wave. So now, talking about since there are different, since wave is a different type of quantity, it has some unique properties. For example, if you consider wave, uh, waves obey the principle of superposition. By principle of superposition, what do you mean by principle of superposition? According to the principle of superposition, the amplitude of a wave, if there are one or more waves, then the due to the principle of superposition, the amplitude of the resultant wave will be the sum of the amplitude of the two waves. So due to this, since the wave has different parameters like wavelength, frequency, amplitude, so corresponding to these things, or if suppose we are considering two waves at a time, then what will be their resultant wavelength, what will be their resultant amplitude? So these things depend upon the nature of superposition of the two waves. Now if the two waves have same frequency and same amplitude, and they are moving in opposite direction, then they form standing wave. So as you can see, this is the example of standing wave. So this is a standing wave. As you can see, suppose this is x equal to 0 and this is x equal to L. So there are two suppose there are two limits here or two boundaries here. Now one wave, if you see the uh, solid line wave, it is passing along x is equal to 0 to x equal to L. So one wave is passing along this direction, and another wave which is traveling this dashed line which represents another wave which travels along this direction. So now if you see, the wavelength of the wavelength of both the waves are same, because if you measure from here to here is one wavelength for this wave, and from here to here there is another wavelength. With this lambda 1, this is lambda 2. So lambda 1 is equal to lambda 2 in this case, and also the frequency is same. So but they are in opposite, so they are traveling in opposite direction. So they are called as standing waves. And in case of standing waves, they form node and antinode. So where the since they are opposite in direction, so they have a phase difference. So where the minima of one wave coincides with the at a particular time or particular position. Suppose here there is variation of position, because at a particular place, the amplitude of one wave is maximum and the amplitude of another wave is minimum. Then in that case, it is called as antinode. And where both the waves have amplitude 0, then this is called as node. So in case of standing wave, we can find node and antinodes. Similarly, for same, if the two waves have same frequency and they have same or different amplitude and they are moving along same direction, here the direction is same, then they undergo interference. So now you can see here, this is the example of interference. So these are two waves. They have in this case, in this example, they have similar. They have same amplitude and they're moving along same direction. So if you see, they have the phase is also same, because at time t equal to 0, the phase is 0 here and the phase is also 0 here. So they are interfering constructively, due to which their amplitude is getting added. So if you see here, this amplitude is twice of the above amplitudes. And so this phenomenon is called as constructive interference. And if in case they have a phase difference of 180 degrees, such that uh, the maxima of one wave coincides with the minima of another wave, then in this case, suppose this is plus s and this is minus s, so it will be 0. So now you can see so the total amplitude is 0 in this case. So so this is called as destructively or destructive interference. So due to interference, we get, if the two waves have same amplitude, then we get maximum amplitude. Or if the two waves have same amplitude and same phase, then we get maximum amplitude, because they interfere constructively. And in opposite case, when they have a phase difference of 180 degree, then they interfere destructively. As a result, we get higher amplitude and no amplitude in two cases. Similarly, if there are two waves and the two waves differ slightly in their frequency, and they have same amplitude moving in either same or opposite direction, then they produce beat. So if there is a phase difference between two waves, or they have different frequency also, then if you solve this equation, suppose now if you see the representation of wave is y is equal to a sine kx minus omega t. So this a is the this is the mathematical representation of a wave. Y is equals to a sine kx minus omega t. Here a is the amplitude of the wave, and it shows that the amplitude of the wave varies sinusoidally. And there are two quantities. We know wave is a function of two quantity. One is space or position coordinate, another time coordinate. So with position coordinate, this a k is 2 pi by x and omega is 2 pi by t. So this is time, this is temporal part, and this is spatial part. Spatial part means related to space, spatial dimension, and temporal part means related to time dimension. So this is the representation of a wave. So now if you see, if the two waves have same or different frequency and then moving in opposite or same direction, suppose one is a sine kx minus omega t and another is, suppose this is y1, then y2 is a sine kx minus omega t plus del. But del is phase difference. So due to phase difference, then they will be having different amplitude. Then there will be having different frequency. So in that case, we get beats. Now, as you can see here, the two waves are in phase. But since there is a change in their frequency at after traveling this point, they are out of phase. That is, they have here the phase difference is, suppose this is the phase difference between two waves. Like here, this quantity is called as phase. Now if you calculate phase here, the phase is 0 in this case, because they have minima at same position. But here, due to their variation in frequency, they have here this is maxima, but for this red color wave, this is minima. So in this case, they interfere destructively, and they have a phase difference of pi. So as you can see here, they form beats. So here the total here there are two types of wave. One is the variation in the fluctuation in their amplitude. Another is the wave when the wave in which the amplitude of the total wave varies. So in this case, we can define phase velocity and group velocity. So if you consider about a single wave, then it will be having phase velocity only. But if you consider about a number of waves, then we call it as, then we can assign some other quantity which is called as group velocity. If you know something about quantum mechanics, then you know that like in case of light consists of electromagnetic waves. Every matter in the universe is associated with a wave, and this is called as matter wave. Like here, this is electromagnetic wave. There are pressure waves. There are like waves in fluid medium. So there are waves associated with a matter particle, and with and if you go to a more detailed discussion, then you can find each matter particle is associated with a number of wave, but there each metal particle is not associated with single wave, but however they are associated with a number of waves. So this is called as wave packet, and this wave packet has a velocity which is called as group velocity. Now in this case, if you consider this case, if you see the group velocity will be 0 because they have formed standing wave, but they have phase velocity. So these are different types of conditions where you can see different types of phenomena if there are two waves. Now let's discuss about the experiment, which is transverse wave in a string. Now if you see, like I told you before some time, if we will take two waves, one is y1 which is equal to a sine ax minus omega t, and we will take another wave which is represented by a sine kx minus omega t plus del, where del is the phase difference. Now according to the principle of superposition, if then y1 y2, if you see, if you put the formula sine a plus b plus sine a minus b like that, then you can find this y will be 2a sine del by 2 minus omega t and cos kx minus del by 2. So now you can see there are two quantities. One depends upon time and another depends upon space. So the variation is different. So like in this case, there is one envelope here and another is this blue one and another is green one. So due to this, they form different types of envelope. Now if you put different types of boundary condition, now if we are talking about in case of standing waves, or like this is the condition when suppose there are two waves like this. This is s equal to 0 and this is x equal to L. So this is the equilibrium position. Now you can put the boundary condition. The boundary condition is y equals to 0 at x equal to 0 and y equals to 0 at x equal to L. Now if you put the boundary condition here, then you will find y will be 2a sine kx sine kx cos omega t, and then putting another bound condition, we can find sine k y is equal to sine kl equals to 0. Now here in this case, so sine kl equal to 0. Now if you compare, sine kl will be equal to sine n pi. Then we can find here L is equal to n pi by k, or L is equal to n lambda by 2 because k is 2 pi by lambda. So this is the expression of length where there will be either maxima or other minima, which is called as nodes or antinodes. So if you see, if n is equal to 1, it is called as fundamental mode. So L will be lambda by 2. So if this is the length L, then L will be equal to lambda by 2. So there will be only one minima or one maximum. So this is the fundamental mode. So n equal to 1, this is called as fundamental mode. So for in this case, L is lambda by 2, because if you see, it will be like this. So this is so lambda is equal to 2L or L equal lambda by 2. Now if you put n equal to 2, then L will be lambda. Then in this case, the wave will be like this. Now here you can see there is two antinodes here and one node here. So this n represents the number of antinodes. So this is, here the antinode is 1, here the antinode is 2. So like this. So this is called as fast overtone or second harmonics. Like this. So if you consider phase velocity of the particle c, then phase velocity is equal to frequency into wavelength, and this phase velocity can be written in terms of, if you consider a string and it has some mass, then this can be considered t by mu square root. Now, if using this formula, we can calculate the mass per unit length, because if you calculate wavelength and frequency, then we can calculate velocity, and from velocity we can calculate this unknown quantity. There, here t is the tension in the string, and mu is the mass per unit length. So now these are a few things related to wave and propagation of waves. Now let's solve a few problems regarding to the propagation of wave. So the first question says, a stationary wave of frequency 30 Hz is set up in a string of length 1.5 meter fixed at both ends. A stationary wave of frequency 30 Hz. So the wave has frequency 30 Hz and is set up in a string of length 1.5 meter. So length is 1.5 meter, which is fixed at both the ends. As you can see, these are two fixed ends. The string vibrates with three segments as shown in the adjoining figure. So now you can see there are three segments, or the three antinodes. The speed of the wave along the string. Now we need to calculate what is the speed of the wave. So these are the informations. We have frequency, we have length, and there are three segments. So we know frequency is equal to velocity by wavelength. So from this length and from this figure, we can easily calculate wavelength, and from frequency and wavelength, we can calculate velocity. So I'll be giving you a few minutes to try it. Please try to solve it and tell me the answer. After some time, I will do it for you if you don't do. Yes, anyone tried to solve it? Can anyone tell me what will be the velocity of the wave? Yes.
So 30 meter per
Anyone?
second. So 30 meter per second.
So let's now solve it. So from the informations given, we can say that the frequency f is 30 hertz and the length, that is the distance between these two fixed points. This is these are the 2 points. This is 1.5 meter. Now, as you can see, the string vibrates with 3 segments as shown in the figure. So here there are 3 segments. Now, if you see n equal to 2, there are 2 segments. So similarly for n equal to 3, so this is lambda by 2. So it will be 3 lambda by 2. So since here L is n lambda by 2, so here n is 3. We know L is n lambda by 2. So here n is 3. So it is 3 by 2 lambda. So what is lambda? Lambda is equal to 2 by 3 into L. So 2 by 3 into L is 1.5. So 2 by 3 into 3 by 2, which is 1 meter. So wavelength of the constituted wave is 1 meter and the frequency of the wave is 30 hertz. So if you use the formula, frequency is equal to frequency f is equal to velocity by wavelength, or velocity will be frequency into wavelength. So it will be 30 into 1. So this will be 30 meter per second. So this is the correct answer, 30 meter per second. So C is the correct answer. Now let's solve the next question. The question says, what is the fundamental frequency of vibration of the string in the above question? So what is the fundamental frequency? So what do you mean by fundamental frequency? So we have already discussed this mode is called as fundamental mode. This mode is called as fundamental mode. And for fundamental mode, we have L is equal to lambda by 2. So in both the cases, velocity will remain the same. So for fundamental mode, the frequency changes, so as well as the wavelength changes. So due to the change in mode or change in the constituent wave, then the frequency will change. Similarly, the wavelength will change, because since frequency and the product of frequency and wavelength is velocity, so velocity is constant, is equal to frequency into wavelength. So since the wavelength will be changing, because in fundamental frequency the vibrations will be uh, with a different frequency as well as different wavelength. So there will be different frequency as wavelength, so that the velocity will be constant. So we need to find out what will be the fundamental frequency of vibration. So please calculate and tell me what will be the fundamental frequency of vibration in this case. Yes, anyone? Can anyone tell me what will be the fundamental frequency of the wave? Let's solve it. Now the question says what is the fundamental frequency? Now we know for fundamental frequency n is equal to 1, and if you put the formula n, L is equal to n lambda by 2, then here it will be lambda by 2. So L, so 2L equals to lambda. We have L equal to 1.5, so lambda is 2 into 1.5 is equal to 3 meter. So lambda is 3 meter. We know velocity is 30 meter per second. So if you calculate, frequency is equal to velocity by wavelength. Velocity is in meter per second, wavelength is in meter. It will be in second. So if you calculate, it will be 30 meter per second divided by 3 meter, which will be 10, will be 1 by second or second inverse. It will be 10 hertz. So the fundamental frequency of the wave is 10 hertz. So this is the correct answer. So now consider the next question. The question says, what is the velocity of transverse wave traveling along a thin copper wire of length 50 centimeter and mass of 1 gram if it is traced by a weight of 4 kg? So we know in the performing the experiment, we have disturbed some straight wire with the help of some mass, and due to the tension in the string, it undergoes oscillation, and due to this oscillation, it propagates between two fixed points and they constitute a wave. So in this case, the height of the wire above or below its equilibrium position changes, and it results in a transmission of a wave. So here the question says, what is the velocity of this of the transverse wave which travel along a thin copper wire of length 50 centimeter and mass 1 gram if it is traced by a weight of 4 kg. So now the weight is 4 kg. Copper wire have the length of 50 centimeter and the mass is 1 gram. So you have these informations. So using this information, you need to find out what will be the velocity of the transverse wave. So you can solve it and tell me what will be the velocity of the transverse wave which is traveling in the wire due to the load. Anyone? Can anyone tell me what will be the velocity of the transverse wave which will be propagating in that way? So let's solve it. So here, what is the velocity of the transverse wave traveling along a thin copper wire of length 50 centimeters? So the length of the wire is 50 centimeter and the weight of the wire, basically it is not weight, it is mass, because weight, the limit, the unit of weight is Newton. This mass is 4 kg. The copper wire have the mass of the copper wire have the mass of 1 gram. So this is the mass of the weight and mass of the wire is 1 gram. Now we know the formula for velocity of transverse wave is given by, for a stress string due to some weight is tension divided mass per unit length square root. So we know tension is mg. So it will be 4 into 9.8 into 500 divided by, this is 1 gram. So 0.001, sorry, 001 divided by 0.5. So this is length is 50 centimeters. So it is 0.5. So if you solve it and the square root of it, so it will be 4 into 9.8 into 500 into 0.5 divided by 0.001 square root, which will give you 140 meter per second. So this is the correct answer. Now the velocity of the propagating wave due to the weight of 4 kg, due to which the wire is stressed, the copper wire of length 5 centimeter and 1 gram mass, and it will oscillate and there will be a propagation of wave, and the transverse velocity of that wave is 140 meter per second. Now the next question is, a wire under tension vibrates in fundamental with a frequency of 450 cycles per second. It's not sound, 450 cycles per second. What would be the fundamental frequency if the wire were half as long, twice as thick, and under 1/4 tension? So here one condition is given, and in that case the frequency is 450 cycle per second. So the frequency is 450 CPS. However, the question says what would be the fundamental frequency, because the fundamental frequency is 450 for a particular tension. If the length of the wire is half of the initial case, the thickness of the wire is twice, and the tension in the wire is 1/4 of the initial value, then what will be the frequency in that case? So try to solve it and tell me what will be the fundamental frequency in the modified case or second case. Yes, anyone? Solve it. Now the question says the fundamental frequency is 450 cycles per second or 450 CPS. So now we know frequency is equal to velocity by wavelength. We know frequency mu is equal to velocity by wavelength, and we know velocity is t by mu square root, and wavelength is and the relation between length of the wire and wavelength of the wave produces n lambda by 2 is equals to L. So lambda is 2L by n. So now for fundamental frequency, we have n equal to 1. Then lambda is equals to 2L. So if you use this for all these quantities in this formula, we can find is equal to 1 by 2L into T by mu square root. So this is the value, and this value is given as 450. Now L will be half of the initial value. So in second case, small l will be L by 2, and the radius is twice, and the tension is T by 4. The radius is 2R, because twice as thick means the radius of the wire is changing. So now if you calculate the mass per unit length, then it will be pi d square into pi d means 2R, pi r square. It is pi 2R square. So then it will be 4 pi r square rho. So 4 into the original, because for original case it was r square pi r square rho. So it is 4 into mu. So the new mu, or the new mass per unit length, is 4 into mu. So if you calculate, then new frequency, new prime will be 1 by 2L into T prime by mu prime square root. So 1 by 2 into L is L by 2. T is T by 4 divided by mu prime. Mu prime is 4 mu square root. So it is 1 by L into T by 16 mu square root. So it will be 1 by 4 into 1 by L into T by mu square root. So if you solve it, it is 1 by 2 into 1 by 2L into square root of T by mu. Now this quantity is the initial quantity, which is 450 cycles per second. So it will be 450 by 2 to 25 cycles per second. So the correct answer is 225 cycles per second. So in question it was given that initially the a wire was vibrating under some tension, and the fundamental frequency of the vibration was 450 cycles per second. But in the second condition, what will be the fundamental frequency? Because the other quantities are other quantities were varied. The length of the wire was varied, which was half of the initial length. Then the thickness of the wire was twice, and the tension on the wire is tension on the wire was 1/4 of the initial tension. So L is L by 2, T is T by 4, and thickness means R prime is 2r. So mass per unit length is pi r square rho, which is pi into in the second case. In second case, mu prime is pi into 2r square into rho. The density remains same, so it is pi r square. So it is pi r square, 4 pi r square rho, so 4 into mu. So the mass per unit length in the second case is 4 times that of the that was the initial case. So these are the quantities. So when you put all these quantities in the expression for fundamental frequency, we get nu prime is 1 by 2L into T prime by mu prime root over. So putting all these values, we calculated the fundamental frequency in the second case is half of the fundamental frequencies of the first case. So it was 450. So 450 by 2, it will be 225 cycles per second. So I think it is clear to all of you. Now, is there any doubt? So now let's move towards the next question. The question says, the radius, density and tension of a string A are twice the radius, density and tension of another string B. If the lengths of the string are equal, the ratio of the frequencies of their fundamental vibration will be what? So the question is very similar to the previous one. In previous one, there are single wire, but the parameter was varying in both the cases. But here there are two wires named A and B, and they have different parameters. So what will be the there we are calculating the change in frequency basically. So here, since there are two wires, so what will be the ratio of their fundamental frequency of vibration? So it is very much similar to the previous question. I would like you to try it and solve and tell me what will be the ratio of the fundamental vibrational frequency, that is Na divided by Nb. I'll give you 3 minutes, then we will solve it again. So let's solve the question. Now we know in the previous question we solved the same thing. The frequency of fundamental vibration N is given by 1 by 2L T by mu square root. Now for where A, R is twice, so it is 2. So RA is 2RB. Density is also twice, so rho A is 2 rho B. Tension and tension of another string B. So tension is also 2. So TA is 2 TB. So and the lengths are equal. So LA equals to LB. These things are given. So now we know this is the formula for fundamental frequency. So now let's first calculate mass per unit length. So mu A will be since length is equal, so it will be pi into 2 RB square into rho is 2 rho B, so it is 2 rho B. So it is 2 into 2 into 2, so it is 8. So it is 8 into pi RB square rho B. So it is 8 into mu B. So 8 mu B equals to mu A. Again, so mu A by mu B is 8. So and tension is, we have the value of tension. Then if you calculate NA by NB, it will be, since length is equal, so it will be square root of TA. So NA is, so it is 1 by 2L TA by mu A square root divided by 1 by 2L TB by mu B square root. So this cancels out because L is equal. So it will be TA by TB into mu B by mu A square root. So this is T is 2 TB. So this is 2 TB by TB into mu B. Mu B is, it is mu B and mu A is 8 mu B. Square root mu B gets cancelled out. TB gets cancelled out. So it is 1 by 4 square root or 1 by 2. So NA NB is equals to 1 by 2. This is the correct answer. So the correct answer will be option C. So 1 by 2. Now the next question. If the frequency of vibration of a string is increased by a factor of 2, then the tension in the string will be what? This is a very straightforward question. Now the frequency of vibration, we know n is equal to 1 by 2L T by mu square root. So n varies directly as the square root of tension. So frequency is increased by a factor of 2. So it will be 2n. Then it will be how much? That will be the tension. For 2n, the tension will be 4t square root because it will be 2 into root t. This is 2 into n. So the answer will be 4 times. Because when t is 4t, n direct proportional to root over of 4t, that is 2t. So n is 2n. So the tension in the string will be 4 times if the frequency of vibration of the string is increased by a factor of 2. Now, a string is vibrating in its fast overtone, then point formed exactly at the middle is. So suppose this is the two endpoints. Suppose this is the two endpoints. This is 0, L. So this will be, this is L. This will be in between. This will be L by 2. So now the question says, if the string is vibrating in its fast overtone, then what will be the point which will be formed exactly at the middle? Now we know fast overtone means n equal to 2, is not it? Because n equal to 1 is fundamental frequency. N equal to 1 is fundamental frequency or fast harmonics. Fast harmonics. And n equal to 2 is second harmonic or fast overtone. So for n equals to 2, so for fast overtone, for n equal to 2, L is n lambda by 2. So it is n is 2. So it is 2 lambda by 2. So 2 gets cancelled out. L equals to lambda. So in this case, is L equal to lambda. So the wave formed will be like this. Now it will again get reflected back. So it will be like this. So in this midpoint, what is this point is called as? This point is called as node. So the correct answer is node. So these are the questions related to. So these are the questions related to the transverse and longitudinal waves and their formation in a stage string, because due to some, if we apply some load, then there is tension developed in the string, and there is a, then the where acts as the spring and they undergo vibration, and due to the change in the height of the uh, where above its equilibrium position or initial position, there will be formation of wave and the wave will travel. So now let's discuss about the next one, which is linear expansion of metal. So here basically the expansion of metal uh, um, as an effect of the change in temperature. So what is thermal expansion? The thermal expansion is the tendency of matter to change its safe area or volume in response to a change in temperature. So we know every matter particle constitutes of atoms and molecules, and they undergo vibration. So when the temperature is increasing means we are providing energy. So if the temperature is increasing, then the mean energy of the particle is also increasing. So they will be vibrating along their mean positions, and due to their movement, then there will be the change in shape, change in dimension of the object. If the object is one dimension, then there will be change in its length. If the object is two dimension, then there will be change in its area, and for three dimensional object, there will be change in volume as an effect of change in temperature. So now if you talk about types of expansion. Now the relative expansion are called strain. Now we had already discussed in case of elasticity, there is strain. Strain means the ratio of deformation to original dimension. So the relative expansion means expansion relative to the original dimension. It's called as materials coefficient of thermal expansion. The relative expansion divided by the change in temperature. So the relative expansion per unit change in temperature is called as materials coefficient of thermal expansion, and generally it is also a function of temperature, because it's obvious. Now there are three types of thermal expansion corresponding to three types of dimensions. For one dimension, it is linear thermal expansion. Two dimension, it is areal thermal expansion, and for volume thermal expansion, it is gamma. Generally, it is dependent on beta and gamma like this. So what do you mean linear expansion? When the heat is applied on a body, its length expands proportional to the original length or change in temperature in the body. So now change in temperature in the body. So now if you now suppose this is a rod which have a length L0 at some temperature T. Suppose T is equal to 0. Now the temperature T is T1. So there will be due to increase in temperature where T1 is greater than 0. So the temperature increased. So the particles constituting the rod will vibrate and there will be increase in the length of the rod. So this is L. So there is some change in the rod. Delta L is equal to L minus L0. Now, how will this change depend upon the parameters? So the change delta L will be direct proportional to L because longer is the rod, there are more particles. So at a particular temperature, there will be more number of vibrations. So there will be more expansion or more relative change. So the thermal expansion delta L is direct proportional to the original dimension of L, and also it is direct proportional to the temperature difference, because if it is obvious that if the temperature is more, then the resultant linear expansion will be more. So this is so the change in dimension is also direct proportional to the variation in temperature. So we can say that delta L is direct proportional to L into T, or if you use a proportionality constant, then delta L is equal to alpha LT. This alpha is called as coefficient of linear expansion. So if you calculate alpha, alpha will be delta L by L into T, or delta L by L divided by T. So delta L by L is deformation and T is temperature. So here it is written, the relative expansion divided by the change in temperature is called material's coefficient of thermal expansion. So this is for linear. In case of coefficient of linear expansion, it is delta L by L. Similarly, the coefficient of areal expansion is called delta B, which is delta A by A divided by T. And for volumetric expansion, it is gamma. It is delta V by V divided by T. So these are the types of thermal expansions. Now, since there are different types of coefficient of thermal expansion, the result, and since if you consider other contributions, then it will be L is equals to L0 and 1 plus alpha T plus beta T square plus gamma TQ, like that. So in case of linear objects, the dimension in case of linear objects, beta will be very small because the length is very large compared to the cross-sectional area. So beta will be very small in comparison to alpha. Then in that case, we can write L is equal to L0 into 1 plus alpha T. So if you calculate it, L minus L0 is equal to L0 alpha T, or delta L by L0 T is equal to alpha, which is the working formula in the corresponding experiment. Now, how the experiment is formed? This is the this is called as PID controller, and with the help of this, we can provide temperature and we can measure. We can heat the system, and again we can measure the temperature. What is the temperature of the other temperature at the equilibrium position? So in between, so within this, there is a rod of which we are calculating the coefficient of linear expansion. There is a micrometer which shows the change in the length. So if you vary temperature here, then there, due to the coefficient of linear expansion, there will be thermal expansion, which will be linear for the rod because the length of the rod is very large compared to area cross section. So it is one-dimensional expansion, which is called a linear expansion. So if you draw graph corresponding to this temperature, if you take temperature along x-axis. So now you see this temperature is along x-axis and along y-axis there is displacement, or displacement is mm, that is delta L. So if you calculate slope, slope m is delta y by delta x. So you can calculate delta L by temperature T. So we know alpha is delta L by T. So this is change in length. Now this delta L by L will be the original length by T. So alpha by T you can calculate, then it will be, so the alpha will be 1 by L into delta L by T. Delta L by T can be obtained from this graph. Now if you see silicon, gold, aluminum, there are three. These graph shows the displacement for change in temperature for three different materials. So for silicon, as you can see, with increasing temperature, its linear expansion is very small. Gold has smaller expansion comparison to aluminum. Aluminum has the maximum expansion corresponding to. So the slope is lesser for silicon. The slope is more for aluminum, or the rate of change of displacement is more with change in temperature when you compare aluminum with gold and silicon. So now let's solve a few questions related to the thermal expansion, linear coefficient of linear thermal expansion. The question says there are three rods A, B, and C of equal length at same temperature. Their coefficient of linear expansion are alpha A, alpha V, and alpha C respectively. If the temperature of all rods are increased by theta degree Celsius and coefficient of linear expansion is like alpha B is greater than alpha A is greater than alpha C, then what will be the final order of length of the rod? So there are three rods A, B, and C. So there are three rods A, B, and C, and they have length equal. So they all have length L. But so for this rod, the coefficient of linear expansion is alpha A, for this alpha V, for C, alpha C. And the relation between these linear coefficients as given. So alpha A, so it is alpha B is greater than alpha A, and alpha A is greater than alpha C. So this condition is given, and you know the formula for coefficient of linear expansion. So by using this formula, you can calculate what will be the final order of length, because in all the cases the temperature is same. So the change in length, the change in length will be direct proportional to the final length, because initial lengths are same. So try to solve it and tell me what will be the sequence of the final length of the COS. What will be the order of length of final condition. So let's solve the question now. The question says there are three rods. They have their coefficient of linear expansion, but the coefficient values are different. The initial length of all the rods are same. What will be the original? What will be the final length? Now we know L is L0 1 plus alpha t. So if L0 same for all, which is L, T is theta degree Celsius, which is also same for all. So if you compare here, L only depends upon alpha, and if you see here, L is direct proportional to alpha. So if alpha is since alpha B is greater than alpha A and greater than alpha C, so similarly LB will be greater than LA will be greater than LC. So this is the correct answer. LB greater than LA greater than LC, because if you see, the final length depends upon three parameters. One is coefficient of linear expansion, initial length, and temperature change. The temperature change and initial length of the wires are same. So it only depends upon the coefficient of linear expansion, and the coefficient of linear expansion varies as alpha B greater than alpha A, which is greater than alpha C. Then if you do the same thing, it will be clearly LB greater than LA greater than LC. So the correct option is option D. Now consider the next question. A rod of length L having coefficient of linear expansion alpha is laying freely on the floor. It is heated so that the temperature changes by theta. Find the longitudinal strain developed in the rod. So the length of the rod is L. So this is the rod. Suppose this is the rod. The length of the rod is L. Expansion is alpha. Coefficient of linear expansion is alpha. And the temperature change is theta. Theta is the change in temperature. So theta is the change in temperature. Then what will be the longitudinal strain developed in the rod? So please calculate and tell me what will be the answer. So we know L equals to L0 1 plus alpha t or theta in this case. So L minus L0. So L equal to L0 plus L0 alpha theta, or L minus L0 is equal to L0 alpha theta. So longitudinal strain developed in the rod is L minus L0 divided by L0, which is equal to alpha theta. So alpha theta equals to delta L by L0. So alpha theta is the correct answer, and this is the longitudinal strain developed, alpha theta. Then question number 9. Find the length of steel and copper rods so that length of steel rod is 8 centimeter longer than the copper rod at all the temperatures. Alpha at all the temperature. Alpha copper is 1.8 into 10 to the power minus 5 for degree Celsius, and alpha of steel is 1.2 into 10 to the power minus 5 for degree Celsius. So there are two rods, one is of copper and another is of steel. They have different coefficient of thermal expansion, but we have to find the length of the two rods so that both the length of the rod will be same, or the final length of the rod will be same for all temperatures. So we need to calculate what will be the length of the steel and what will be the length of the so here it is given. There is L steel and L copper. Suppose L steel is, find the length of, so that length of the steel rod is 8 centimeter longer than the copper rod. So if copper rod is X, the length of the steel rod is 8 plus X centimeter. This is 8 X centimeter and this is X plus 8 centimeter. Now we need to find the length of both the rods so that they will be having same length at every temperature, because the coefficient of linear expansion is different for both the cases. So you try to solve it, and after some time I will solve it for you. Let's solve it. Now it's given that the initial length, so the length of the cylinder at all temperature. So what are the initial length? So that at any point of temperature, at all temperatures, basically the difference between two length is 8. So suppose this is the initial length L0. This is L0. Now we have, so this is sorry, this is final length. Now these are the initial lengths. These are L0s. These are the final lengths. And now we know L equals to L0 1 plus alpha T. So L still will be L0S 1 plus alpha S T, and L copper will be L0 copper 1 plus alpha copper into T. Now it is given the length of steel rod is 8 centimeter longer than the copper rod. So length of steel minus length of copper will be L0 plus L0 alpha ST minus L0 CU. L0 S alpha ST minus L0 CU minus L0 CU alpha CT. So this is the equation. Now LS minus L copper is 8. This is L0S plus L0S alpha ST minus L0 CU minus L0 CU alpha CT. Now this is the case. Now what we will do, so it is given at initial stage, that is L0S minus L0 CU equals to 8, and at any other position the length are same. So the change in length, what is the change in length? The change in length we know, the change in length for steel is L0S alpha S into delta T, which is equal to the change in copper L0 Cu alpha Cu delta T. Delta T is equal in both the case. So L0S alpha S equal to L0 Cu alpha Cu. Now we know alpha S is how much? Alpha S is 1.2 into the power minus 5. So it is suppose it's 1.2 into 10 to the power minus 5, and alpha C is 1.8 into 10 to the power minus 5. So we can say that LOS alpha is 1.2 is equal to L0C 1.8. So L0S is equal to 18 by 12 L0C, or we can say L0C is equals to 2 by 3 of L0S. Now this is one equation, and this is another relation. So if you see here, L0C is, so basically we can write it in this way. So if you put here L0S minus 2 by 3 L0S equal to 8. So 1 by 3 L0S equal to 8. So L0S is equal to 24 centimeter. So this is the so we what we find L0 S minus L0 Cu is equals to 8 and L0 C equal to 2 by 3 L0 S. L0 C equal to 2 by 3 L0 S. So L0 S minus 2 by 3 L0 S equal to 8. So 1 by 3 L0 S equal to 8 or L0 S equal to 24 centimeter. So L0 S is equal to 24 centimeter and L0 Cu is equal to 24 minus 8 equal to 16 centimeter. So this is the correct answer. So the correct answer is option A. So here it was given that the length of the copper, initial length of the copper rod, we need to find out the initial length of the copper rod so that at all temperature, the final length of the steel rod is 8 centimeter longer than the copper rod. So these are the calculations. So there will be two. So if you compare, since at all temperature the length is equal, so change will be equal. So since the change is equal, we use that condition and we calculated, and the correct answer was length of the steel is 24 centimeter and length of the copper is 16 centimeter. Now the next question is a circular hole of diameter 2 centimeter is made up of the diameter of 2 centimeter is made in an aluminum plate at 0 degree Celsius. What will be the diameter at 1000 degree Celsius, where the linear expansion of aluminum is 2 × 10⁻³ per degree Celsius. So we know L is L0 1 plus alpha T. So L0 is 2 centimeter. Alpha is 1 plus alpha is 2 into 10⁻³ and T is, this is not 1/3, this one is degree, so this is 100 degree. So 100. If you calculate, it will be 2, 1 plus 2 into 10⁻³ into 10⁻². So it will be 2 into 1 plus 0.2. So it will be 2 into 1.2. It will be 2.4 centimeter. So this is the correct answer. 2.40 centimeter will be the diameter of the 2.40 centimeter will be the diameter at 2.40 diameter 100 degree Celsius. Now the next question. A bimetallic strip is made up of aluminium and steel. On heating, the strip will remain straight, get twisted, will bend with aluminium on concave side, will bend with steel on concave side. So now this is the case. One is suppose this is steel and this white part is aluminum. We have alpha of aluminum is greater than alpha of steel. So what will happen on heating? So on heating, we know L equal to L0 1 plus alpha T. Since alpha Al is greater than alpha steel. Now here initially L0 is same. So the change will be direct proportional to alpha. Like in previous case, we are calculating delta L is direct proportional to alpha. So since alpha Al is greater than alpha steel, so delta L aluminum will be greater than delta L steel. So this is the, suppose this is the length of aluminum and this is the length of steel. So the aluminum will be larger and steel will be smaller. So what will it look like? So how it will look like? So if you see, initially both were same. Both were of same length. Now it increased, the aluminum part increased more, the steel part increased less. Is not it? Sorry, steel part is, let me see what is so aluminum is white, steel is, so aluminum increased more, steel increased less. So this is steel, this is aluminum. Since both the ends are connected here, so they will bend. So how they will look like? They will look like this. Because it is smaller, so it will be lying inside. If the twist is like this, then this will be steel and this will be aluminum. So this is convex side, this is concave side. So will bend with aluminum on concave side or will bend with steel or concave side. So what is the correct answer? The correct answer is steel on concave side. So as you can see, this is concave side. So steel on concave side, because the expansion of steel is lesser than that of the expansion of aluminum. So the radius of the curve will be more for aluminum and less for steel. So it will be lying inside and in the concave side. Is there any doubt in this question? Anyone? So today we discussed all these things. In next class we will talk about a few more experiments. We'll start with determination of coefficient of thermal conductivity of a bad conductor. So in the previous in this class we talked about the formation of formation of standing waves, longitudinal waves, and transverse waves. We knew about waves, the types of waves, and how the waves are formed, and we and we studied about the studied about the property of linear expansion of metal, and we solved a few problems regarding the coefficient of linear expansion of metal. Now, I will like to stop it here. In the next class, we will discuss other experiments along with we'll solve a few problems. So thank you all for joining in today's session. Good night.